Okay, so here is 10:20, so I think we can start. Hello everyone, my name is Maciej Gajdzica and I'm here today to talk to you about safety critical systems from the perspective of a developer. So first, let me introduce myself a little. I am talking to you right now. Wait a minute. Okay, sorry for that. So I am talking to you right now from Gdańsk in Poland. Where I am working for Solvit, and I am an embedded software developer. And during the last 5 years, I had experience with a few safety critical projects from the areas like railway, automotive, and medical. I also like to share some of my thoughts about software on the internet. So I am running a blog and YouTube channel, both in Polish, and I am also organizer of embedded meetup in Gdańsk. At least I was before the lockdown. So from this perspective, I am even more impressed by the organizers of NDC Oslo that they made that happen, that they went online. And I'm also happy that I could be part of it. Okay, so let's start like proper engineers should. So first we want to define our problem. So what is safety critical system? The easy definition for safety critical system is that this is the system which, in case of an error, can have some dramatic consequences. Maybe some people could die. Maybe we can pollute the environment, or we can damage some expensive equipment, or we could destroy someone's property. And we don't want all of these things to happen. So while designing and operating those systems, we must take some special measures to make sure that nothing wrong will happen. Okay, so we know now what safety critical is. Now let's think for a while what it isn't. So first of all, there's a difference between safety and security, because safety focuses on preventing the device to do harm to people, and security is basically preventing our device from people that want to make harm to it. And of course, there is some common ground for safety and security, because if attacker takes control of our device, and this device is part of nuclear power plant or airplane, we have huge risk of the accident. But those two fields have also some things that are not common for safety and security. Also, safety is not the same as reliability. Probably you know some systems like in banking, which just always needs to work. They have availability like 99.999% and things like that. They couldn't lose any transaction. If part of the system stopped working, they should be able to handle this properly. And in some circumstances, safety critical systems are doing exactly the opposite, because if we suspect that something wrong may happen, it's better for safety critical system to shut down in a controlled fashion than to let it work and risking some accident. Okay, now let's take a look into some some simple examples. This is kitchen blender, and this blender have some sharp knives. So the risk here is that we could cut our fingers. So how we could solve this problem? We have button, and for this blender to work, this button must be actively pressed all of the time. If we stop pressing it, the knives will stop turning. So we cannot accidentally turn it off. We cannot leave it working and start doing something else. So by this simple solution, we are dramatically decreasing chance of the accident. Now take a look Now take a look on another example. This is a fire starter for the barbecue. And here we also have a risk. We can burn everything down if fire gets out of control. And the solution is here is to make it almost unable to start the barbecue, almost unable to light a fire. And this is example of bad design, because we might think that this is really clever idea, right? We cannot do anything wrong if we don't do anything. But as a side effect, our product also is useless. So users try to overcome this issue, and they are making another risks. But the whole idea that if we don't do anything, we cannot do anything wrong is still valid. And we also use it in safety critical systems. We have this common pattern called safe state. And the flow of events is something like that. We detect that something is wrong, so we set all of the outputs of our device to some state that it cannot harm the environment. And then we go into the endless loop, so we are sure that those outputs won't be changed. And in this state, we wait for the operator for decision. Maybe he wants to restart the device. Maybe he wants to replace it with another one. But the really important thing is that nothing wrong will happen before this operator will do something. Okay, there are many different areas where safety critical devices are used, and not every device, in case of error, have the same negative consequences. So the safety norms created something like safety integrity levels. So for every level, there is a set of best practices that we should follow regarding the project. And if we have really critical project, we will have to do more techniques to providing safety than if our safety level is lower. And also for lower level of safety, we really don't want to use all of those techniques, because they will make our project longer, more expensive, and harder to do. So here on this table, you can see levels from different fields like railway, aerospace, and so on, and possible causes and possible consequences of the accidents. So the highest level of safety must be ensured where death of many people is possible, and then we have levels with lower risks. Okay, but how we can prevent our devices from making errors? I want to start with some simple system where we have engine that is doing some critical task, and this engine is fueled with gasoline, and we also have a valve that is controlled by our electronic device. And this device is measuring how the engine is doing its work, and it's controlling fuel input to the engine. And now, imagine that our device stopped working, so it can no longer control the valve. So this valve will be set in some default state. And we have two possibilities now. This valve can be fully open, so we allow fuel to be added to the engine, and we lost control of our device. But the default operation can be also to shut down this fuel intake, and this way the engine will stop by itself, so the system will be still safe even if our device will stop working. This ability is called fail-safe. So our element is fail-safe if even if it's not controlled, it couldn't do any accident. And we can abuse many laws of physics for our advantage. In wolves, we are using mainly gravity, but there are also many other examples. For example, if we have a ventilation system, and in case of fire, we can lower amount of air that is flowed to the fire, so we will stop it from spreading. And for example, in railway signaling system, if our control device stops working, by default, we say that track is occupied. So we minimize the risk that some other train will come and will crash into the train that is on this track. There are also many other possible accidents and threats that we must think of. And one of this is hardware errors of our processor. We have many parts in our processor and in our device. We have RAM memory, we have non-volatile memory, we have CPU with registers and some logic gates and transistors that are responsible for doing operations. We have clocking systems, interrupts, and so on. And any of those parts could be broken, could fail. And we must somehow prevent that from happening. So now I will discuss a little how we can prevent clock errors. Because if we are controlling some critical systems, it's really important that if we want something to last for 1 second, it's really 1 second, not for example, 10 seconds. So how we can do this? Of course, we can use some external clock sources and compare this. But one of the best approaches to this problem is to use redundancy. So we can have two processors that are doing basically the same, and they are sending to each other a square wave. And this square wave have some predefined timing constraints. So we know for how long long signal and low signal and high signal should take. And if you measure signal that we are receiving from the other processor, and we see that this timing is not fulfilled, we have two possibilities. Maybe our device is counting time correctly, and we received malformed signal. So we expect that second processor have damaged clock. And the other possibility is that the signal we are receiving is correct, but our device have problem with clock. And we don't need to investigate further which one is right and which one is not. The conclusion is that we have error in our device, so we should take proper action. We don't need to know what exactly happens. We just need to prevent the accident. And this redundancy concept is all over the safety critical devices. We have, for example, this concept of two separate channels that are doing basically the same. So we have channels that have a separate set of inputs, of sensors. They have separate processing path, and they have separate outputs. And they are exchanging data with each other. So we know that the data differs between them, and they can detect errors and act accordingly. We can have even more sophisticated redundancy mechanisms, like this voting mechanism. So here we have 3 separate channels and some mechanisms to decide which output is correct. And this concept is widely used, for example, in aerospace, where we can't just go into some safe state and wait for the operator. We must ensure that the airplane which is in the air will safely land. So if one of the channels will be broken, we still have 2 other channels that can outvote this broken one, and we will still be able to proceed. Of course, we can use any combination of those redundancy mechanisms, like two separate channels with voting systems inside, or voting system consisting of duplicate channels. We can use many other combinations. Another thing that I want to focus on is communication, because as you saw with this redundancy, we must communicate with many blocks, and this communication also needs to be safe. And what you see here is a table from the railway norms where someone did the threat analysis and proposed a solution to this. So we have this analysis as a normative reference, so we don't need to do everything from scratch while doing communication. We can just read the document and fit it into our need. So if we have communication, we have a lot of possible threads. We can, for example, duplicate our communication frames. We can lose them. We can reorder them, or we can have even man-in-the-middle attacks. And there are some standard ways of dealing with them. We can add sequence numbers. We can add some handshake mechanisms. We can add encryption. And every defense is protecting us against some threats. And the second part of this analysis is dividing networks in some categories. So we have here three different categories. First one is that we are doing communication inside our device. So there is no risk that someone else will enter this communication, and we have full control of every node in the network, and this network have fixed topology. So this is the easiest case, and there are not that many risks in this case. We have also a second category where we can have network consisting of device that we fully control, but it can be reconfigured, it can be dynamically changed. So here we have other risks because there's a bigger possibility, for example, to receive frames out of order and so on. And we have also a third category where our network is fully open and basically everyone can join, and we don't have control over the nodes. So in this case, we are exposed to a lot of threats, and we must take the biggest measures against it. So we have some documents that are suggesting us what should be done for every level, and we can use this analysis to our advantage. And regarding communication, there is other interesting problem, because imagine the situation that we have two safe processors that are communicating with each other, and they are also doing some more critical tasks. And we must implement this communication protocol on the same processor that is doing this critical task. And let's imagine that we are using TCP/IP stack. So we must implement all of the layers. We must implement buffers for frames. We must handle all of the layers of this communication. And this is some complex piece of software. And the problem here is that we can make mistake. We can leak our memory. We can have a deadlock. We can use too much CPU time. And by doing this, we can affect this critical operation. So if we are doing this thing on the same processor as something more critical, we must use the same safety measures like for the most critical part of our code. And in case of TCP/IP protocol, this is really a problem, because most of the implementations that are available doesn't meet those requirements. And we really don't want to write TCP IP stack from scratch. So what could we do in this situation? And the solution is quite clever. We can move our TCP IP stack to another processor and use some easier communication protocol to communicate between the communication processor and safety critical processor. And this way, we separate the critical part from non-critical part. And we can treat our communication processor as part of the transmission line. And really, we are doing this assumption with many other devices in Ethernet networks, because we have switches, we have routers, and we just treat them as transparent, as part of the network. And this way, we can use we can use third-party libraries with our communication stack and implement only a smaller part, which is much easier to do. And this concept of moving things into another processor to make it easier for certification and to separate some things that could threaten our critical tasks is really common in safety critical systems. It's called mixed criticality systems. And here you have another example. So we have one processor that is doing critical task, that is controlling the engine. And we have also a second processor that is responsible for handling communication with user. And we have control panel consisting of graphical interface, of touch panel, of some buttons, some sound signals, and all of those things are not that critical, but they use a lot of resources, a lot of memory, a lot of CPU time. And if they are on the same processor, we will increase the risk of failure. So it's better to separate them and make our life easier. Another thing that I want to talk about is how we can deal with data corruptions, because data corruption may happen because of many things. For example, we can have some programming errors in our devices. We can, for example, have stack overflow. We can go outside of bounds of array. We can use pointers incorrectly and override some data. So there are many possible software errors that will corrupt our data. But the data is the memory is a piece of hardware, and there could be also some hardware issues, like, for example, changes because of power supply noise. The bits could be stacked on the single value, and we can even have cosmic radiation that will change our bits. So in the most critical systems, we should somehow ensure that our most critical data are not accidentally changed. And how we can do this? In this example, we have two data regions where we store the same variable. In the first region, we are writing the normal data, and in the second region, we are doing negation of every bit. And before any use of our variable, we must check if XOR operation is resulting in 1 on every bit. And if by accident some memory is changed, there is really low possibility that it will change both memory regions in a way that this precondition is still fulfilled. So this is the mechanism that will help us detect some memory corruption. But when I first heard about this, I wondered how it is done in practice. And this document had some example code which looked somehow like this. And I was quite disappointed because we have two different variables. And by the way, this is code written in C. We have two different variables, and we must do these checks manually, and we are adding complexity to every simple read of the variable. So if we do everything right, maybe we will increase our safety. But the risk of making mistake by doing everything manually in the code is huge, and probably it can negate all of the pros of using this technique. But we can do this better. We can use some simple mechanisms in the code that probably everyone knows that can make our life easier. First of all, we can just use some abstractions. If we move our checks into the function, we can proceed with those variables in more easy way, and we don't need to bother about checking everything every time. And we also could use our compiler to find any issues. We can use, for example, modifiers of variables like const in this situation. So if we by accident overwrite the pointer, we will have the compiler warning. We can also use constant variables for the same reason. So in this case, we can only change the value that is pointed, but we cannot change the address that we store in our structure. So we are using the language mechanisms for our advantage. And this is the introduction to to the languages that we are using in safety critical systems. Basically, we have two approaches to languages. First of all, we can treat developers as smart people that never make any mistake, that knows what they want to do, and we should just go out of their way and they will create software that is working correctly. And this is philosophy and C or C++, which are most common languages in embedded systems, but also in safety critical. And we have other approach where we know that developers sometimes don't know what they are doing. They could make mistakes and they can do something by accident. So we must have a language that will prevent us from doing some mistakes. And here the best example of such a language is Ada, which is used widely in aeronautics or in military. And Ada have some cool features that are protecting us from many mistakes. For example, we can define our types with custom ranges. So we don't need to use, for example, 32-bit variable and check if it's in range. Compiler will do this for us. We can even specify if we want overflow in our variable or not. And regarding arrays, we also have ranges for index, so we cannot go out of bounds. Even if we are not a real programmers and we start our index from 1 and not from 0, we can easily do it in Ada. And by the way, we can start from any index, so we can handle offsets more easy, because compiler will do this calculation for us. We have also strong types. In this example, we have two types. One is for meters and second is for miles. And they both have the same underlying type float, but they are different types because they are storing values that are not compatible with each other. So we just cannot use both of those variables in the same calculation. We must explicitly cast them to show that we know what we are doing, and this is really what we are trying to achieve. You can find more information about Ada if you are interested. There is a website called Ada Core where you can find tutorials, where you can find free ebooks, and you can just check this language and try it. Another thing about languages is how we can prove that our code doesn't contain any errors. Because in the 60s, Edgar Dijkstra said that tests cannot ensure us that our code don't have any mistakes. If our tests are passing, we cannot be sure that we don't have any mistakes. We only are sure that if tests are failing, we have some errors, but it's not working other way around. So Dijkstra tried to do some formal proofs that code is correct, and he were doing some things like in math, like we are examining some mathematic formulas, and he tried to do the same thing with software, and he could do this only for really simple code, and this cannot be used for production level applications. But we have something called Ada Spark, and this is a subset of Ada which claims that it can ensure that codes don't contain any runtime errors like uninitialized variables, like exceptions, like null pointers, and so on. And also to ensure that we are fulfilling the functional requirements, and this is done by some syntax for design by contract. So we basically state in the contract what we are trying to achieve, and then compiler will check if the function is really doing that. And to make it possible to check if our code doesn't contain any errors, we must have some limitations. For example, we shouldn't do recursion. We shouldn't use nested loops. We should have only one exit point from the functions, because this all makes analysis of our code more easy. And as I said before, Ada is not the most popular language in embedded and in safety critical. We still use mostly C. We also use C++, but this idea of having language subsets that make our code easier is even more needed in C or C++, where we can shoot ourselves in the foot in many ways. So we have language subsets like Misra C or AutoSAR C++. Okay, now let's talk about some formal requirements and some documentation. What you can see here is the project workflow for safety critical systems called vModel. And as you can see, it's very detailed, very formal. We have a lot of different phases. And regarding documentation, we have some documents that need to be created on every level. And as you can see here, there's a lot of paperwork. And one downside of safety critical systems is that documentation is an integral part of the software. We just cannot release our software if it's not properly documented, because it will not fulfill certification. So we must ensure that our documents will be done, and they will not be, and it won't be that painful. And I saw some projects. Some had good documentation, some had useless and outdated documentation, some didn't have any documentation at all. But I saw some things that are working and not working. And first of all, the thing that definitely doesn't work is to leave all of the documentation at the end of the project. And we have some simple rules that could make our life a lot easier. So first of all, we can make documentation part of the code review. So we check that code we are reviewing is doing exactly what is written in the documentation, and we cannot merge into the master branch anything that is not documented in our design documents and in our architecture. And another possibility is to use something like in TDD, where we write tests before our implementation. We can also write documentation before implementation, at least part of it, or make it more interactive, because this is really what we do when we are designing our software. We are thinking what we want to achieve, and then see how we can do this. And by writing it down, we can make our lives a lot easier. And actually, this technique is used, for example, in open source, where we have RFC, requests for comments, and this is just working. And regarding some formal restrictions and documents, there is also another interesting area, version management. You probably know semantic versioning of our binaries, but here in safety critical devices, we must track the version of every binary that we are using in our device, of every hardware element of our device, and we must also track bundle of all of this together to track the version of the whole device. But this is not the end of the list, because we must also track versions of tools that we are using, like compiler, even operating system, some tools for testing, for configuration, and so on. So this way we are minimizing the risk that something is working on my machine but not on yours. But this has also another purpose, because we must be able to rebuild our binaries from source for the whole lifetime of the product, because we must be able to fix any problems that will occur, and we must also investigate issues, and we must be able to do so for the whole lifetime of the product. And the downside of this is that this lifetime of the product could last 20 years. I don't know if you think if it will be possible to compile your project 20 years from now. And I think it's really challenging task to do so. And here is the screenshot of some code editor from 20 years ago. So here we can see what advancement we done in the industry, and this will be just hard for us to use those tools anymore. Okay, and this is not everything about tools, because there is also another thing. We must ensure that every tool that we are using for development of some most critical systems is okay for this job, that we can trust it. For example, that compiler will every time create the same binary, and so on. And in most restrictive fields, like for example aerospace, sometimes we also need to have certification for our internal tools needed for development, like, for example, testing frameworks, like, for example, configuration generators. And we have this inception here, because we must certify tools to use certified software, and we can go deeper. And another thing I want to talk about is human factor. Here you can see the quote for Nancy Leveson, which is one of the biggest experts in safety critical field. And this is what she said about people and processes, that insisting that people will always follow some procedures doesn't guarantee that our systems will be safe. It only guarantees that there will be someone to blame. But the real interesting part is at the end of this code, because we can blame those people either for not following the procedures and for following them. So if they are operating the system when something bad is happening, they are just screwed. Okay, and this was comment to some model that is used for modeling accidents. And this is model that everyone probably knows. This is root cause analysis. So we have some outcome, some accident, and we want to find what was the root cause. And we assume that there was some action that started chain of events that led to the accident. So we must have this terminator mentality and ask why. So we know the accident happened. We have some clues. So we try to find the answer for the question why that happened. And we know that something else happened earlier. Then we also ask why, and we end up with some root cause. And this root cause could be, for example, someone who are not following procedures, but it also can be bug in the software. Also, it could be some problem with hardware part that was broken. And this model of action and reaction is really not useful for making better products after we find out the solution. They are really most useful to lawyers who can charge someone for the accident, that we can find out who is guilty. But the problem is that we still can ask why we had software bug, why someone didn't follow the procedures, why we have hardware parts that failed. And it will turn out that in real world, our systems work, and all of the processes of development are working more like feedback loop, where we have also some things on the organizational level, like communication between parties, like some procedures that we are following and our attitudes toward those procedures. If those procedures are hard to follow or well understood. And all of the things in isolation are innocent, but one action will amplify another, and we can have this feedback loop that is amplifying some behaviors. And if our procedures are dysfunctional, we will we'll have more and more risks over time, and the root cause of the particular accident may be technical, but the real reason is almost always on some organizational level. And this concept was described by Nancy Leveson in the book Engineering a Safer World. And I would also I would recommend this book. You can read there about some examples, not only about software, like for example, some chemical facility that had a leak and the servicemen were charged, or we have some examples from the military with procedures for friendly fire. And there's also another book that I would recommend. This is What Do You Care What Other People Think? This is a set of stories from Richard Feynman's life, and half of this book is describing investigation of Challenger accident, and he described here how the organizations works and some details of some problems on organizational level. And also, if you saw TV series Chernobyl, probably you noticed some problems, like for example, deadlines, like not hearing any feedback from someone on lower levels, like trying to hide some information. It was all in this TV series. So, but how we are dealing with this today and in real projects? Not great, not terrible, I would say. Probably you all heard about Boeing accidents. And first we heard that some part of the plane didn't work properly. And then we heard more and more information that something was wrong during the development, that some things were not done properly. And if you want more details, I put the link to preliminary investigation report about Boeing, which is really interesting read. But this case was really famous, so almost everyone heard about this. But I want to show you some other things that happened in recent years. I don't know if you know about this incident. A few years ago in Hawaii, there was a nuclear missile alert because of some problem with testing procedures on ballistic missile facility. And part of this alert is this is not a drill, but fortunately, actually, this was a drill. Another example is accident of two ships, one oil tanker and one US Navy destroyer, which crashed in Singapore Strait. And the reason was that the destroyer rapidly changed its course and went into path of the oil tanker. And the pilot of destroyer were accused for causing this accident and killing some crew of the ship. And after some further analysis, it turned out that the control panel was flawed. It was using some touch screens which were not which were complained by the pilots. They reported that it didn't work properly, that they set some settings by accident, that sometimes they even want to switch it off and go to manual control. And of course, we can force people to follow some procedures, but if it's too complicated, they just cannot be followed. So here we have really some other problems that wasn't addressed. And how we can deal with those things on the organizational level. What you can see here is also taken from railway norms. And these rectangles are roles in the project that couldn't be shared. So for example, someone who is project manager couldn't be also developer or tester. If someone is for the project, he even cannot be under the same project manager as testers and developers. So this way we are trying to increase efficiency of our product by having different goals achieved by different people. So if validation is not under project manager, this project manager is less likely to force some decisions. And for assessment, for certification, the best approach for most critical systems is to have a different company doing this. Those dotted lines are the boundaries of the companies. So if assessment is done by another company, we are minimizing the risks because other company don't have those deadlines, don't have this financial pressures, have different stakeholders. So by separating those concerns, we hope that the checking will be done better. And this is really important to stick to those boundaries, because if this will be flawed and we will have some pressures, we can compromise the whole system. So to conclude my presentation, I tried to show you that there are some great pieces of software engineering that describes some techniques which can make our software more safe. And we should just read what is already discovered, and we can increase safety of our systems this way. But this whole effort will don't have any effects if we don't do proper things on higher levels, if we don't have good enough communication, if we are achieving correct goals, if we are not pressing for rushing for some things, and we are not making some voices not heard. And this is all that I wanted to show you on today's presentation, and thank you for your attention. Also, I will share my slides on Slack channel, so you will have the possibility to check those links and check the slides. If you have any questions, I think that we have a few minutes, so maybe you can raise the hand or say something in chat, and I will try to answer now. Okay. First question is, do you use any kind of formal verification, model checking methods for TLA plus that is in your current job as a safety critical system engineer? Okay, so now I am working for a project that don't have this highest level of safety, so I don't need such techniques. But I was working on one system which was critical, and this worked this way that there were some person in the project who was a safety engineer, who was responsible to do some analysis And for example, in case of communication, because in that system the communication was the one of big concerns, he had some probabilistic models of errors, and he could, for example, use some mathematical formulas to decide which CRC polynomial or what length of CRC we should use to fulfill some safety requirements for communication. So I don't know about those techniques that you were mentioned, but in most critical application, we had some dedicated people that were analyzing this and sharing with developers. And also one of the other techniques that is very useful is to do some kind of risk analysis. So every time during the development we see some things that may go wrong, we can add it to some list, and then we should discuss on some kind of meeting what are possible consequences of this risk. Should we take any measures, and which measures are enough? And we should document this and have some kind of risk document pointing out all of the risks that were identified and considered. Okay, another question. Okay, can he talk about how to avoid the safety system being the part of the failure? I think that part of the problem I addressed during this part with root cause analysis and feedback loops, because, for example, if we treat all of the failures as separate things, we might not have some, we cannot see some other things that may impact those behaviors, like, for example, deadline pressures or things like that. And actually, the best way to avoid a situation where this safety critical system is part of the problem is to use the simplest solutions that we could. So, for example, if we can use hardware solution and software solution, it's better to use hardware because it's more reliable. That also it fails in some probabilistic fashion that we can predict, and it doesn't have some undefined behaviors. So actually the simplest solutions are preferred to make it less complex.